Okay, I'll do that. Okay, so today we do some more solving equations by factoring. We got to learn a little bit more about factoring that we didn't already do. Most of the factoring we do in this class is really in chapter 4, what we've already done. But there's the new pattern that we haven't seen is sum and difference of cubes. And then we have to learn about this thing right here that's called the fundamental theorem of algebra, which sounds like a very important theorem. Right? It's the, not a fundamental theorem, it's the fundamental theorem. There's also a fundamental theorem of arithmetic. You know what the fundamental theorem of arithmetic is? If you have two numbers, they're either equal, one is greater than the other, one is less than the other. They got to be one of the three. So, anyways. So first we're gonna warm up by doing another one of these exercises, right? Let's put the data in the calculator, see what it looks like, choose the appropriate model to make a function. Right? If you are unclear, remember, we go to Stat, Edit, and you put the data, the X values are under the L1, the Y values are under the L2. A little more air than that. Remember, you know, your calculator's been used all day to do the same thing. So they're probably already turned on for plotting of points. If they're not, remember how to turn on the plotting of points? Second y equals is stat plot, right? And make sure that it says on right there. If it's not on, then hit 1 and make sure that it's highlighted on. Hit enter, right? Then how do you make the calculator go to your points? Zoom 9. Because if, for example, if I just went to the middle of the graph, zoom 6 for zoom standard, let's see, y equals clear. If I went to the normal graph, I wouldn't even see my points, right? But if you go zoom 9, which is zoom stat, then it takes you right to the points that you put in the calculator. So now, what kind of function does that look like? It looks like it's linear, right? So go ahead and make a linear model. How do you do that? Stat, arrow over to the calc, pick linear, which is 4. Yours has a little bit different screen, but get down to the calculate, and when you hit enter, you get that, right? Okay. If you've gone through that whole process, right, so you did make this regression equation. I mean, the equation looks like that. I rounded to 2 decimal places. What if we had to use our model to estimate values of y for x equals 18? You plug in x equals 18, right? What if, and you wanted to estimate for x equals 40? Plug it in, right? But remember, you can have your calculator do that for you by going to the calculator and on the y equals, right? Make sure that it's clear before you start, and then remember these steps. Vars, 5 for statistics, because everything was under stat, right? And then which one do we choose there? EQ for equations, right? So when you scroll over there, the first line, that says regression equation. That's the thing you just made. If you didn't make one, you wouldn't get that there. But if that's there, then when you hit enter, it puts it on y1 equals. It doesn't look like it, but look what happens when you hit graph. It draws the line right through the points, right? That is the best fit line, the regression line through those points. Couldn't draw a better line through those points. Okay, now if you wanted to find the value of the function when x equals 18, go to the table of values, right? Just go to second table and scroll down to x equals 18. Although, I'll tell you, for you guys, I'm going to say this, that for me, I wouldn't do that. If I haven't shown you this before, here's another thing. I would go to the table set, which is on top of window, right, and go second table set, and I would set it to ask, right? Go down and set it to ask, enter, and now when I go to my table of values, it's blank, and I can put in 18, I can put in 40, or any other value that I want, right? Instead of having to scroll through numbers when they get kind of big. Okay, first you go to second window for the table set, and you set this one, independent, set it to ask. Because remember, x is the independent variable. And then you go to second graph, which is the table of values, but it'll be blank until you give it some x values. Okay. Okay, then let's review this thing. So part of the homework tonight will be a worksheet where you do the same thing, right? On one side of the worksheet, it's this already filled in. On the other side, it's not, and you just try to repeat what you've seen. But remember, we did three things when we did this the other day. We did the intervals of increasing and decreasing. We did the zeros, and we indicated what they call end behavior, right? What is the graph doing on the ends of the graph? Okay, for the intervals of increasing and decreasing, you've got to be able to look at a graph like this and say that notice that it is increasing on that part of the graph until it gets to this point. And then it's decreasing because it's going down, and then it's increasing because it's going up. Right? When you label the intervals of increasing and decreasing, it always means the intervals in terms of x, not the y values. It's the y values that are going up and down. Right? But these are intervals of x. So for this interval, it's increasing from the left side of the graph until it gets to which x value? -1. So you would say that it's increasing for x less than -1. And it's increasing starting here and going to the end of the graph. So you would say it's increasing for x greater than 1. And it's decreasing in between -1 and 1, right? And you say that by going -1 is less than x is less than 1. Right? This one, right, it was decreasing from this end of the graph until it got to, looks like -3. So you say decreasing for x less than -3. It's increasing in between -3 and what x value? 0. So you say increase for -3 is less than x is less than 0, right? And then it's decreasing from this point to, what is that x value? It's 4, right? Don't look at the -4, look at the +4, because it's x, not y. So it's decreasing from 0 less than x is less than 4, and then it's increasing from this point onward, x greater than 4. Okay, so that's that. Where do you look on these graphs for the zeros? The x-intercepts, right? So the next part of this that you'll have to do on the worksheet, just circle all the zeros. Circle, 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 circle. Easy. Only one there, 2 there. And then the last thing is indicating the end behavior, which again, you could do this in different ways, and different books do it in different ways. We'll just do it like this textbook does. This textbook just uses the words up and down. So it would say on the left side of the graph, down. On the right side, up. Right? This one would be up and up. It's going up. At the ends of the graph, right, it's going up and up. Right? What's this one doing? Down, up. And how about the last one? Down and down, right? Down and down. Okay, so that's going to be part of the homework tonight, to be able to just do that. Probably won't take you a few minutes. Okay, next we get into the factoring again. Remember that we factor in order to solve equations. For example, if we have an equation here, x squared minus 5x plus 6 equals 0, that's the standard form, right? In standard form, if you tried to isolate the x, you couldn't do it because the x is in two terms and they're not like terms, no way to put them together. So we factor and we get x minus 3 times x minus 2 equals 0. Now we can use the zero product property, right? Since this product equals 0, it must be that one of the factors equals 0. Okay, just like the homework from last night. What are the zeros of that expression? 3 and 2, right? That's why we learned to do the factoring. Okay, these were the different methods that we used so far. What does the GCF stand for? Greatest common factor. Okay, then we had difference of squares like this, right? How does x squared minus 4 factor? X plus 2 times x minus 2. Right? And then we had the simple quadratic trinomial. What made it simple? Yeah, remember that the standard form of a quadratic is ax squared plus bx plus c. And when the a is 1, we call that simple, right? That's like this thing right here, right? Because the a was 1, we just had to take one step to factor it. We didn't need the 5 steps, split up the middle term and all that. You don't need it. Right? Because that's a 1, it's a one-step process. The not simple would have been the a does not equal 1, like the one we did over there. And then we had perfect square trinomial. Okay, the new ones that we do today are what I'm calling GCF plus, which we kind of did in the last chapter. It means that we'll start with a GCF and there'll be a little bit more to do. And then the sum and difference of cubes, right? Those are definitely new methods for us today. What's that? You don't have to write anything. Right? We ready? Not much on there. So here's the greatest common factor plus, what I'm calling it. And so you look at, here's your polynomial equation to solve. Is there a greatest common factor? X. Every term has an x in it. So factor it out. Okay, now what's inside parentheses, is that factorable? Can you think of factors of negative 54 that add up to negative 3? Negative 6, negative 9? You're close. Negative 9, positive 6. Okay, so we put it in a factored form, and then we can say what the solutions or the zeros are. What's the solution from this? 0, 9, negative 6. Right, if you looked at it on the graph, right, there's the negative 6. Kind of hard to see the 0, but it is going straight, almost straight up and down on the axis there. And then there's the 9. You know, if you're not sure, go to the table of values, right? Second graph, and what are you looking for? You're looking for where y equals 0, right? Because y equals 0 on the x-axis. So you look for negative 6, 0, 9. Okay. Okay, how about this one? Any greatest common factor? Hint, yes, there is. Okay. 3x squared, right? Because the lowest power of x is 2. So everything's got at least x squared. So we could factor out the 3x squared. And then what's left in the parentheses? Okay? So now, look at your greatest common factor. What's the 0 that comes from that? 0. Remember, it's not x plus or x minus anything, so 0 is the 0, right? So here's, for this one right there, it's x equals 0. But it's not just that, right? It's got a multiplicity. What's the multiplicity? It's mult2, which means what in terms of the graph? It means that the graph is going to come down and it's going to touch that 0, but it's going to go back on the same side, right? Because that factor will not change sign on either side of x equals 0, because you're squaring it, right? That's what we expect from a 0, which is raised to an even power. Okay, that's why we study that. Now, for the what's in the parentheses, you got to first ask yourself, is it factorable? Can you think, it's simple quadratic. Can you think of factors of 4 that add up to -2? Come on, the factors of 4 are pretty simple, right? 1 times 4, 2 times 2. Or -1 times -4, -2 times -2. Do any of those add up to -2? No. So it's not factorable. So how else can you solve it? Say again? Quadratic formula, right? Remember, quadratic formula is the one you've got to use. If you can't think of any other way, use it. It'll always work. And specifically, when you see that this graph does not look like it's crossing the x-axis again, that means the other zeros are probably imaginary. And where do imaginary zeros come from? The square root of a negative from the quadratic formula, right? So definitely this is a quadratic formula case. So let's do that. X equals -2 plus or minus the square root of -2 squared minus 4 times 1 times 4 divided by 2 times 1. X equals 2 plus or minus the square root of -12 over 2. Right, 4 minus 16, -12. So sure enough, we can see this is going to be imaginary. The solutions are imaginary at that point. How can I simplify the square root of 12? Remember, square root of 12 is not a perfect square, but does it have any factors that are perfect squares? 4 times 3, right? So break it up into 4 times 3, and then you can take the square root of 4, 2 root 3. So we can simplify this like this, right? That will be 2 plus or minus 2i times the square root of 3 divided by 2. And then what else could you do now? You got 2's everywhere, right? So you could factor a 2. This 2 divides evenly into that 2 and that 2. It basically cancels them both. So that is, what does that leave? That leaves 1 plus or minus I root 3. Right? So if there are real zeros, they're going to show up as x-intercepts in some respect, right? If they're not, then they're not going to show up as x-intercepts. You have to solve for them. And how do you solve for them? Quadratic formula. Okay. Okay, that brings us to sum and difference of cubes. Okay. So by the sum of cubes, it means the sum, the addition of two things that are cubed, right? And difference of cubes, it's a subtraction. And we have two formulas. They're almost the same, just a little different. Notice, first of all, that it's a binomial times a trinomial, right? It's got to be a binomial times a trinomial. There's a lot of times when we get down to taking tests that they're going to give you something like that, and they're going to give you multiple choice answers that are not a binomial times a trinomial. So they're not right. It has to be a binomial times a trinomial. Okay. Now, in order to do this, we need to first, let's represent, we're going to do x to the third plus 1. Let's write that as the sum of cubes, because right now it's not. Right? But how could I write 1 as a cube? X to the third plus, what number cubed equals 1? 1, right? So now I've written it as something cubed plus something cubed. In our problem, what is it that represents the A and what is it that represents the B? The X equals the A and the B is 1. So in this formula, everywhere you see an A, substitute with an X. Everywhere you see a B, substitute with a 1. Right, so that'll look like X plus 1 times X squared minus 1X plus 1 squared. Right, just substituting for X and 1. Right. How about the X to the third minus 8? What number cubed equals 8? What number cubed equals 8? 2. 2 times 2 times 2 is 8. So we can write it as X to the third minus 2 to the third. Okay, so what is it in our problem that represents the A? X, and what is it that represents the B? 2, not negative 2, right? The negative is part of the formula, right? So that is taken care of by the formula. It's always a positive. You're never plugging negatives into these formulas. So now just follow along. Everywhere you see an A, put an X. Everywhere you see a B, put a 2. So this one will be X minus 2 times X squared plus 2X plus 2 squared, which is 4. You know, you should try to memorize the formulas, and then, you know, you don't look at them like they're different. They're actually very similar. Just notice the differences between them, right? If it's the sum of cubes, then that binomial is the sum, right? If it's a difference of cubes, then the binomial is the difference, right? These match, plus and plus, minus and minus, right? And the only other difference is that and that. You know, they switch. So if that's a plus, that's a minus. If that's a minus, that's a plus. Everything else is the same. Okay, how about, we already said that 8 is 2 cubed, right? How about 27? 3 cubed, right? Now we need to write this as one whole thing being cubed. 8x to the third is not something cubed. The x is being cubed, the 8 is definitely not being cubed. In order to write it as something cubed, you've got to write it like this. 2x in parentheses cubed. That cubes the 2 and cubes the x. Right, so that the whole first term now is something cubed. And then the 27 cubed is 3 cubed. Right, you can't do it with the 8x to the third. It's got to be something that is being cubed. That's why we had to substitute with 2 and put it in parentheses with the x. Okay, now what is it in this formula that in our problem that represents the A? 2x, and the B is 3. So substitute everywhere. 2x plus 3 times 2x squared. Now I'm going to take 2 steps for this. Minus 2x times 3 plus 3 squared. Right, that's just substituting everywhere for A and B. Now you still got to simplify. Right? This 2x in parentheses squared is 4x squared. And then the 2x times 3 minus 6x plus 9. Okay, how about what number cubed is 64? 4. 4 times 4 times 4 is 64, right? So that we can write this one as 4x to the third. Okay, and what number cubed equals 125? 5. So that's 5y cubed. Okay, so now using the formula, right, our a is 4x, our b is 5y, substitute. 4x minus 5y times 4x in parentheses squared plus 4x times 5y plus 5y squared. So I'm going downhill. Okay, simplify. 4x minus 5y times 4x squared is 16x squared, right? No more parentheses. How about the 4x times 5y? 20xy. And how about the 5y squared? 25y squared. There's usually on the SLLs probably like 3 problems that deal with this. It may be a factor problem, or it might be a solve an equation and it's clearly a sum or difference of cubes. The truth is that by the time we get to the SLLs, you'll have some strategies to get problems like that right that don't have to do with you actually remembered the formula. At this time, we're not going to just start resorting to strategies, which are really good for multiple choice kind of things. We'll get there. I'm not worried about that part of it at all. Now, in order to recognize the kind of problem you're being asked to solve, you really need to know the perfect cubes, right? And, everybody should be pretty good with 1 through 5. 6 through 10, maybe not so much, but 1 through 5, definitely. And if you're not familiar with them, remember that you could make your own table of perfect cubes easily enough in your calculator, right? Just go to the y equals. First, let me set my table set back to 0 or 1, enter, auto. And now I'm going to go to y equals, and I'm going to make that x to the third. X to the third. And then when I go to my table of values, there's all the perfect cubes. So if you're not, comfortable with recognizing those, then, right at the very beginning, write down the 1 through 10. And when you see those numbers show up, it's probably because it's something like a sum and difference of cubes. It's a clue to how to solve the problem. Okay, so let's do a solve by factoring. And this one's clearly a difference of cubes, right? And that's x to the third minus 2 to the third, and that factors, I think we already did this one, x minus 2 times x squared, second, plus 2x plus 4. Okay, so what is the solution that's going to come from the binomial? X equals 2, right? And if you look at the graph, you definitely see, right, there's your 2. Right? You can confirm it in the table of values, but x equals 2 is one answer. Now, what do we know about the shape of a cubic like that? It should have how many turns in it? 2, right? A cubic could have 2 turns. And if you look down here, you got your 2 turns, which means this graph is never coming back around. There's only that one real 0. The others have to be imaginary. And when you're solving sums and differences of cubes, what's in the trinomial, the last factor, is always imaginary, always. There'll be one real solution, the other 2 will be imaginary every time. Okay, so let's do a quadratic formula, which is, I think what we did in in a past problem when we were solving, we had x squared minus 2x plus 4. So it's almost the same problem. I'll go x equals negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 4. These numbers are familiar. 2 times 1. So x equals negative 2 plus or minus the square root of negative 12 over 2. So the only difference between the one we did before was that because that was a minus, that first number was a plus. Now it's a negative. So we solved this one already. This one is negative 1 plus or minus I root 3. Okay, which brings us to the imaginary root theorem. Says that if you get solutions or zeros or roots, the truth is that when you're talking about functions, you call these things zeros, right? Because functions are y equals. So asking for a zero, saying what are the values of x that make y equal 0? When you're solving an equation like the last one, this was never a function in the first place. It's an equation. It doesn't have zeros. It has roots, right? And you can use them interchangeably. Most people do without really realizing the distinction between the two. But again, this imaginary root theorem is telling us that because these imaginary roots come from the quadratic formula, you're never just going to get one. You got to get two. Right? If you get negative 1 plus I root 3, like we did on the last slide, you've got to have negative 1 minus I root 3. They come in pairs. Those are called conjugate pairs because these numbers are conjugates. When the only thing that changes in between them is the sign from a plus to a minus, conjugates. So we know that our imaginary solutions will always come in pairs, always an even number. We're done? We're done? For Curtis? Go, hurry up. Okay. Which brings us to the fundamental theorem of algebra. The fundamental theorem of algebra says that polynomials will have exactly as many zeros or roots as their degree. Okay, some will be real, some will be imaginary, but the total number of complex zeros, and I meant to say many complex zeros, will be whatever is the degree. So for example, linear has a degree of 1, so it'll have 1 complex 0. Quadratic has a degree of 2, so it'll have 2. Cubic has a degree of 3, so it'll have 3. Whatever is the degree, that's the number of complex zeros. That's the easy part, right? Then you got to figure out how many of them are real, how many of them are imaginary. How many complex zeros would a quintic have? 5. Quintic means to the 5th power, 5. I don't remember if I delete. You're done? Shane? You ready? Okay. Isis? Almost. Okay. Okay, so the number of complex zeros, real plus imaginary, is the degree. The number of real zeros is taken from the x-intercepts on the graph. Okay, but remember, you got to take into account the multiplicity, right? Because sometimes one x-intercept might lead to more than 1 0, right? So take into account multiplicity. Okay, and then if you can figure the number of real zeros, then you subtract the number of complex minus the number of reals, and you should have the number of imaginaries. Right? It just, you know that the number of imaginaries has got to be an even number. If it's not an even number, then something went wrong. Almost done. Okay. Okay, so the homework problems, there's going to be 4 like this, right? And it'll work just like the directions are just like that. You want to do the same thing. We're going to go a little bit further with it, but it's not in the homework because actually you need a calculator to do some of this stuff, and you don't have a calculator, not a graphing calculator to do it. But this stuff you can do without a calculator. For example, if I looked at number 34, what is the degree? 3. So what are the number of complex zeros? 3. Okay, it has to be 3. Now, up here it's saying what's the possible number of real, and then, you know what, that doesn't even say what I think it says, but what's the possible number of imaginary zeros? 2. Okay, it's got to be an even number less than or equal to 3. So how many even numbers you got less than or equal to 3? 2 and 1 is not an even number in this universe. Okay. So if there's 2 imaginary zeros, how many real zeros are there? 1, because they got to add up to 3. Right? If there's 0 imaginary, how many real are there? 3. So the possible number of real zeros are 1 or 3. Okay. How about number 36, because that's a different degree. 4th degree, so how many complex zeros? 4. Right? And how many imaginary could there be? 4, 0. Right? It could either be 4, 2, or 0. 4, 2, or 0. Which means if there's 4, how many real zeros are there? 0. If there's 2, how many real zeros are there? 2. And if there's 0, how many real zeros are there? 4. Right? That's how you find the possible number of real zeros. Now, actual zeros, let's say we put this one into the calculator and look at the graph. Y equals clear. All right, I'm doing the number 34. X to the 4th. Get out of the exponent. Minus x to the 3rd. Get out of the exponent. Somebody got a phone? 5x squared minus x minus 6. Graph. Okay, so in this case, if I'm looking at this thing, it's a quartic, and I'd expect it could have how many terms in the graph? A quartic could have 3 terms, right? So you can kind of see them all right there on the graph. How many real zeros do you see? 1 and 2. So there's definitely 2 real zeros. How many imaginary must there be? 2. They got to add up to 4. Right. So the actual for number 34 was 2 and 2. I'm just to show you the actual. Okay. Now, what about this one? This is a 5th degree polynomial. So how many complex zeros does it have? Right. This is not possible. It's actual. It has 5, no matter what. Okay. And what would you say are the possible number of imaginaries? It could be 0, 2, or 4. Right. All the even numbers less than 5. Okay. If there's 0 imaginary, how many real are there? 5. Right. And if there's 2, there's 3, and if there's 4, there's 1. Right. Those are the possibilities. Now, look at the graph. How many real zeros do you see? So you would think that it's 1 and 4. Not exactly correct, okay? Remember what it means when it goes through the graph. It doesn't mean that the 0 and the factor are there to the first power. It means that they're to an odd power. And in fact, this one is f of x equals x plus 1 to the 3rd, x squared plus 25. So the -1 is the 0, but it's to an odd multiplicity, and that's why it's going right through the graph. So you can't always just look at it. It's easy like the last one where we could see all the terms, so we were very sure. But a 5th degree polynomial, I mean, that could have up to how many terms in it? 4. And you clearly don't see 4 terms in that graph. Yes. Here? The total number of zeros is 5, right? The zeros have to be either imaginary or real. Okay. The imaginaries have to be in even numbers because of the conjugate theorem. So if they could either be 0, 2, or 4. If there's 0 imaginary, there's got to be 5 real because 5 plus 0 is 5. If there's 2 imaginary, then there's got to be 3 real because 3 plus 2 is 5. Right? And if there's 4 imaginary, there's got to be 1 real because 1 plus 4 is 5. Does that explain it? Okay. In fact, this one was 3 real, 2 imaginary. Okay. So that's what we did. We looked at the sum and difference of cubes. Those are the learning intentions from the SOLs. And then we talked about this is what the SOL actually tells us we have to do. Given a polynomial equation, determine the number of real solutions and the number of non-real solutions. What do they mean by non-real? Imaginary. Okay. Okay.